Hello, hi. I've not, I don't have the right, yeah, the lights on. All right. So I was a little worried, if I had asked whether I had turned the back lamp at the back on. So that's good. All right. So I'm back. And first of all, I'd like to show you before I go into some analysis with the help of reference books, etc. The values I got for, this. Okay, so let that be there. So this was my the Michaelis-Menten plot. Substrate, two different concepts, substrate concentrations, and so these are all the experimental and from the plot values from the plot. So now the you all know I made a mistake yesterday. V naught is equal to V max multiplied by substrate concentration divided by Km plus substrate concentration. So I substituted as instead of Km, Vmax itself, Vmax multiplied by substrate concentration divided by Vmax plus substrate concentration. That is incorrect. Km comes in. So with those calculations, I have so these are this is organic with pressure, inorganic with pressure. So experimental so there's a huge difference. But Michaelis-Menten V naught follows a certain pattern despite the substrate twice the substrate concentration. So for organic with and without pressure, both the values are pretty close. So I guess that is because with sodium lauryl sulfate, the alkyl sodium ion, ion, that's consistent with theory. The alkyl sodium portion, it becomes a positive ion, and then the rest SO4 2 minus or SO4 minus stays, and turns into sulfur oxide, dioxide gas, and that sort of thing. So I was having some, and I never measured sulfur dioxide, right? I could measure. So those two, and these are for the inorganic compounds with pressure, without pressure, and these are these are the Michaelis-Menten. And one more, and I have to add, and of course, a Lindbergh plot may work better for the lower substrate concentrations and for the twice the amount. So half a teaspoon, 1 teaspoon, and so the other factor is that I have considered only the measured mass, right? For the plots. And I showed you the plots and not the mass concentrations as for the S1, S2 parameters, which is mass by volume. That's a mass concentration, gram per mil. So I have not considered that. But for the S1 and S2, I have considered the mass concentration. But the substrates or mass by weight by volume concentration, to be precise. But the substrate solvent volume is 30 mil for all the observed products. So it evens out, right? And then product is 0 at T equals 0. So there's no sulfur dioxide, there's nothing. I did not subtract the substrate mass from my measured products quantities, but the S1, S2 do not change except with the reaction. But, that would be hard. That need an online measuring setup, and it takes periodic samples and measures immediately, and then but so it's usually done with subtracting and that sort of thing, a rough ballpark figure. Definitely I had gaseous products because of the values, and study from Quatten and Wilkinson, third edition, Wiley Easton. So first I've said, before the start of the experiment, that proteases or peptidases are hydrolases. So this book says sodium ions in solution have a hydration radius of 2.76 angstrom and a hydration energy of 406 kilojoules per mole. But it's minuscule per mole, right? I mean, it's minuscule, so it's probably, what, depending, it could be higher for the sodium bisulfate for the inorganic product. So the former would determine the right dimensions of the sodium ion, that the hydration radius, being able to penetrate the active site of the enzyme, and dimensions are high. Dimensions of enzymes are high, but the active site is, maybe three amino acids. I'll show you a beautiful picture, which I may have shared in the past from James D. Watson's Molecular Biology of the Gene. So average amino acids, but average amino acids radius is high. So this is able to go in, right? The substrate, and the hydration energy would add to the heat of reaction, of the sodium ion getting converted to a sodium hydroxide, whatever, or just the sodium metal. Who knows? I mean, but so it may be a high, NaHSO4 is equal to Na plus HO4 HSO4 minus. So on a more organosodium compounds, looking at my organic compound, sodium lauryl sulfate, C12H25 SO4 minus in Na plus. The same reference says that sodium alkyls can be used for metallation reactions. So you can generate sodium. Organosodium compounds are all essentially ionic and are not soluble to any appreciable extent in hydrocarbons. They're exceedingly reactive, being sensitive to air and hydrolyzed vigorously by water. So water was, there, and both are soluble in water. So Morrison and Boyd, Organic Chemistry, Allen and Bacon, fourth edition. A soap molecule has a polar end, COO minus Na plus, or here OSO3 minus Na plus, and a non-polar end, the long hydrocarbon end. The polar end is water soluble and is thus hydrophilic, of course. The non-polar end is hydrophobic. So then moving on to Horton et al. So I have Km. Km is the ratio of the initial concentration of substrate at half maximum velocity. No, sorry, is the initial concentration of substrate at half Vmax by 2, right? Whichever intersects the curve. The plotted curve, S substrate concentrations versus V naught, the slope of the dP by dt reaction. So dP, the product versus time curve. So that's V naught, velocity of reaction, and where Vmax would be a little above the hyperbola, which is formed. That's what my reference says. But I took it a little close. So there could be a bit of a factor there, really close to the, as I showed you. So here it's a little too close, right on top. So you have to give a bit of a gap. And then that's the hyperbola. So K cat is equal to Vmax by E total. I have a value for E total, and I'm pretty positive that it was the proteases reacting. None of the other enzymes reacted. So Km is a ratio of constants for breakdown of ES, that's the enzyme substrate complex, and constants for its formation. So Km is equal to, you all know from Horton et al. Those of you who have taken biochemistry courses, E total. So from this, you'll probably this all stands to theory. It has to be because Km is typically a positive value. ES, the enzyme substrate complex concentration, is negative, which means that it's going into the enzyme. The substrate is going into the enzyme, and enzyme plus product comes out. So it's it's negative. It's in the opposite direction of the product formation. So it's beautiful, isn't it? And more so. Here for me, I had half a teaspoon, 1 teaspoon, so two S1. I could actually get a S1, 2S1. Could get some kind of value here, or I would even out. I think have to substitute one km value. Then I could calculate the other km value, but I have already done all that. So that's pretty cool. And then ES must be negative. If entropy increases with increase in pressure, but mixing parameter was lower, right? When I did the hand waves of the fan, delta G is equal to a delta. That's about 2.54 centimeter cube per second or something like that. The waves I got because roughly I was moving 3 inches. So 9 inch cube per minute, 60, 60 counts. So per minute. So that comes up to about some 2 point something centimeter cube per second. So delta G is equal to, of course, Gibbs free energy, the thermodynamics of the enzymatic reaction. I'll come to it again from in James D. Watson. For the sodium being possibly formed, I always get scared when a purulator or a to my home. Just as I'm sorry, it's just that the universe. No, it's something else. It's a parcel. Okay. All right. So that I don't know. Maybe they get a lot of spam, so they're always strict with me. People all around. Yeah. Maybe I worked hard. So this is this way. This you can see. This is different pens. So this is organic without pressure. Without pressure. So the blue is organic, and it comes still here. Organic 1, and twice the substrate, a half a teaspoon. Organic 2 is green, and goes this way. So this portion is right at at so once the reaction is becoming a little unpredictable after a point, and then the red is inorganic, and there's of course sulfur dioxide which can be measured, and the ink blue is going this way, and this is with pressure, and for twice the inorganic inorganic substrate, the pressure is, this is actually 25 minus the reactant point. So complete reaction, complete conversion. And I don't think there's a lot of SO2 formed here. Why is that, I wonder, with the addition of pressure? Whereas this is consistent, inorganic um, this pressure, inorganic P1, it's okay. It's twice the substrate concentration. Just maybe pressure helps because same thing. Arrhenius equation, right? You all know the Arrhenius law, and oh, where did it go? Delta G is the covalent bond. Enzyme substrate complex is a covalent bond, and then this is so K equilibrium is equal to minus E delta G, Gibbs free energy, divided by RT. So Gibbs free energy can be related to activation energy. So again, Gibbs free energy pressure is so if I were to substitute the equation for Gibbs free energy there, delta H minus T delta S entropy, then divided by RT, then you could have a whole new law going there, but it's already done, so it can be a whole new law. Pressure for a higher substrate concentration gives a really high product formation, and which means that the enzyme substrate complex likes the yeah, covalent bonds are formed more easily. The enzyme substrate complex is a covalent bond. That's what the book says. And the strong bonds actually. So it means that the substrate turning into product and detaching itself out of the enzyme is all force of law, God, force of nature, which is very good. And so pressure. So I suppose I could, do my own pressure substitution there for T. But in for the universal gas law constant, pressure is PV equals nRT. Pressure is directly proportional to increase in temperature. Increase in pressure is proportional to increase in temperature. But um, it may it but it may not be the right thing here. So what else did I want to say? Lastly, um, so pressure. So some law I thought I would come up with, but I could assign you that, and both of us think together. And next time I run an experiment, could do that. I could come up with a law. So I'm going to observe this a little for a little while longer, and see. But the peaks are the same. So the dark ink, the ink blue, there are two peaks here as well, but it's just higher with the pressure addition of pressure. It's an interesting system to study, isn't it? With what I have, there's only so much I can do. But in a university lab or a company lab, I mean, the micropipette assay has taken me so far, because the micropipette tray comes in really handy. You're not decreasing each time you're drawing a sample, you're keeping it at a steady level because each has a different sample. It's more work, but it's more accurate results as well. So I guess pressure increases. But in an enzyme catalyzed reaction, increase in entropy may not necessarily be conducive to more product formation, because or is it not? Again, I have no idea, because pressure increase is showing more product formation. So more molecules moving around, and simultaneously the enzyme substrate complex is being formed all around. So it's all, it's not just one enzyme substrate complex, I think, but there's only one active site in an enzyme. So it's just, interesting, at play here. But an enzyme, how much did I have? I had a minuscule quantity, as always. Catalyst is a minuscule quantity. So one after the other. Yeah, the covalent bond is formed, enzyme substrate complex goes in, comes out as product. Again, enzyme substrate complex is formed, goes in, comes out as product. So every single minute, this is happening. So mixing parameter is also, a huge factor, because micromixing is always a key factor. The more you stir, the better. And so it was all good. So I had a good time. A lot of work. I'm ready to drop. I need a nap before I go. And can you see this? That's my son's record player. I said he, got it. It was gifted to him 4 years ago, and he may have made up in his own way, but he has to listen to it, and his friends are eager for him to get back to him. All right. So signing out, Gayatri B. Sitaram. Thank you.